Okay, so now we should have access to the lab. It is called binary classification, and that is what we are covering today. Yesterday, you all had introduction to some simple machine learning algorithms locally with what was it? You guys were trying to work with numbers in some way, digits, right?
Yep, classify
Handwritten.
handwritten digits.
What was it exactly? Like how? Like what was the goal?
Uh,
We're
for
given,
day one.
Yeah.
Yeah, we had a bunch of images of handwritten numbers, and we trained a neural network to identify them.
Okay, okay. Right, interesting. And you guys were using, what were you using?
PyTorch.
Yes, you use PyTorch, and we'll use a bit of PyTorch today as well. And we'll also be using, oh, that's what I was looking for. MNIST. That is, we all were using yesterday. Today we'll be working with, instead of that, with a very simple binary model. And the difference being you had 9 outputs yesterday, and today we'll only be working with one. What else are we doing today? Let's recap a bit on neural networks. Can someone tell me in their words what a neural network is?
A neural network is, a neural network basically mimics the neural network of the human brain. Initially, what you have within the neural network is the input. And from the input, you have several nodes, and those nodes involves individual processes
Mhm.
perform some action. In this particular case, I'm assuming the action is basically OCR, optical character recognition, where this particular node is going to try to determine specifically what this handwritten character might be, a handwritten note or a handwritten number might be, right? And
Mhm.
from that determination, it either says yes or no in a sense, and then it passes on to the next neural node, which form the same processes until it makes a determination as far as what that particular character might be.
Mhm.
That's just one single example, but the neural network in itself, again, contains nodes that performs individual processes.
Okay. So what makes that so different from like, let's say, an automation or a pipeline, which also essentially consists of different steps or different nodes in a process?
Well, I believe my understanding is the key difference is decision making. Well, as far with automation basically performs a blind action. It just performs the same action over and over and again. But with what makes a neural network unique is actually the last step, which is the last step, which is not loss log, but the way the model trains itself is that it's self-determining, right?
Hmm.
Where at a certain point in time, if the it uses basically a loss algorithm to determine whether the node itself is correct, and then it self corrects itself.
Yeah. Yeah. Pretty much that is the key point. With a neural network, we have a way to learn over time, just like the way the human brain does, or is at least supposed to. And there are various ways that we could do this. On its own, there are the parameters that are internal to these algorithms, and then there are the hyperparameters that we, as the developers or engineers, can tweak and fine tune to adjust things like its learning rate or its accuracy, etc. We could change things like weights and biases in the various layers of our sequences, and we can utilize techniques like back propagation to adjust, pivot and adjust based on past performance. Did uh, It's like A/B testing. Did approach A reduce errors or did it increase errors, etc. And we have access to all sorts of different activation functions. I think we've been using ReLU both yesterday and we'll be using it today. Sigmoid is something else we'll be using today, and that's essentially just something to squash a number into a range between 0 and 1. And we're working with that because our goal today is to familiarize ourselves with binary classification. And that means with just one output, probability. We are taking data inputs and we are going to output into a value between 0 and 1, and that is our probability. Anything from 0 to 0.5 is likely to be a no, and anything that is above that is likely to be a yes. And this is useful for all sorts of real world examples, would be things like loans. Does this customer qualify for a loan or not? Um, what other examples are there? Somebody, I'm not feeling creative today. What other examples do we have for probability? Screening tests, positive or negative, or I'll go on.
You could do whether or not you want to target advertisement to customers.
Yes, exactly. Yeah, and so today basically we'll look at following a similar pattern to what we did yesterday. We'll be setting up a Jupyter Notebook. We'll be setting up various steps, and we'll be talking through some of these techniques that we use to output a probability. I don't know exactly how Jonathan went about this yesterday. I know we talked about it a bit at the start of class today, how a lot of this can feel out of place. We've been focused so much on mixing both DevOps practices and development, and now we're just shifting into essentially data science, and it could be a very jarring shift. We're not expecting everyone to become experts at all of this, to memorize all of these different functions or mathematical equations. We really just want you to get a grasp, to at least feel like you're confident enough in your idea of like what's going on here, because what we want to ensure that you feel comfortable with essentially is the sequence, the step by step of this all, right? You could always look up what ReLU is later on or what sigmoid is later on, but understanding what's happening step by step is key. That's going to be key for understanding a process that we'll be repeating over and over for the rest of the module, and one that we'll be using when we work with SageMaker at the end of it. So yesterday you worked with sequential. It is basically a neural network model that allows you to run different algorithms in a sequence, hence the name sequential. Today we'll be working with module, which is a very generic sounding name, and that's intentional because it is a generic name. Sequential is itself a type of module, and we're working with the base of that, the module itself, because that's going to give us some flexibility. We could define our own class that instantiates this module, and we can design how we interact with it. So in this instance, we specify exactly how many layers we want. What are these layers? We're going to use linear to take inputs and generate these outputs. And then we are going to have methods like a forward pass that will run PyTorch, ReLU algorithms like ReLU and Sigmoid through PyTorch to give us the result that we want. So this is giving us full control, or at least the illusion of control. And we can add anything we need, like conditional logic, skipping certain connections, additional inputs. Your imagination is the limit. The reality of data is it's never clean. So yesterday you were working with pristine data, more or less. But today we'll be working with public data sets. There should be, if there's not, then you could probably just extrapolate from here. There is a link for a data set that we're grabbing. This one, for example, is water potability. Am I just sharing looks like I'm just sharing this window, so can I pull up a browser here? Yes, cool, let me do that. I'll pull up some links later. We'll look at this repo. There's a lot of different data that you can play around with. And so that's going to be essentially today's challenge to grab the notebook that we built and to tweak it around and play around with other data sets. So again, let me drop that link off inside of Zoom. So data sets, there's a repo here with just a bunch of data sets. You can also go on Kaggle. I don't know if Jonathan talked about Kaggle yesterday. I think Chad's talked about Kaggle a few times. If you have trouble setting up Jupyter notebooks on your machine, sign up for Kaggle and just use it in your browser. Where is the Zoom chat? There's Zoom. Where's the chat? Okay. So this repo should have a bunch of data sets they could play around with. We'll be working with this basic water potability for the example. Right. Data sets are never going to entirely be clean in the real world, which is why we have to have different ways to clean that data or optimize that data. Some common strategies would be for missing values, either just dropping that value altogether, excluding it from your data set, or filling it with statistics. And maybe one of like the best starting points is to just use a mean or average value of the data of that column wherever you need it to. And we could do that very easily with methods like fill NA. And we could just pass in inside of this method the mean of the data. And we'll do all of that mathematical magic for us. Other things you could do to normalize various parts of your data set. We have standardization, and that's basically where you're standardizing the way that you measure the data. It wouldn't make any sense to try and compare miles to meters, right? You want to convert into the data set, the data type that you want to use so that you have some consistency and standards across the data. It just makes it easier to work with. It makes it more predictable. It makes it sensible. If you have data that operate and are governed by like different rules, different systems entirely, then you're gonna have to do a lot of additional programming gymnastics to get the data to give you accurate results. And we want to avoid that. So we have handy dandy methods to do that for us. So here we're using sklearn's pre-processing to import the errand scaler, and it will run that magic for us. Splitting, training, and testing. When you train your model, a good practice is to separate the data set into training data and test data, because that's how you can validate the results of the training. It's similar to if your AWS exam had the exact same questions as your practice exam, then that's not a very great final exam, right? Because it could reward rote memorization. Whereas if the data that you're testing the model on is data that it hasn't been trained on, then that is a more accurate way of inferring whether or not it's giving you the results that you want. So with this, we can use another sklearn model, or library method, whatever, model selection, and we will use train test split from that. What numbers do you use to split? Well, it's kind of arbitrary. And again, as more of a hyperparameter, it's something that you could adjust and tweak and play around with in order to get the results that you want. A very good starting point would be 80-20, just like what is it, the Pareto principle, the 80-20 rule. Generally, what the first 20% is what gives you like 80% of the results. And then you'll see diminishing returns from then on. And we'll actually see that later on too when we run math plot lib, the math library for plotting your math. What else? We are going to be converting to tensors. And again, I think if it was covered yesterday, tensors are really just sets of data, right? So we are going to convert to tensors so that we have a predictable way to work with the data sets. What else? I don't know. Can anyone tell me how you all used cross entropy loss yesterday?
It was built into the lab,
Mm-hmm.
but wasn't necessarily detailed.
Okay.
Well, that's how a machine learning algorithm learns. It essentially the loss represents the difference between the actual value
Mm-hmm.
and well the loss represents the difference between what you're actually trying to accomplish. I'm sorry, I'm trying to get to a thought. It the loss again represents difference between the actual value and what you're looking for, basically.
Mm-hmm. Okay. Yeah.
Or
Oh, no,
no,
go
no,
ahead.
it represents the error upside, the error between the actual and the predicted outcome. That's what I'm trying to say. Between the actual and predicted output.
Okay.
That's what the law represents. And the closer the algorithm reduces down to the gradient or the loss gradient, the more it actually represents the predicted value.
Okay. And that is a way better explanation than I can give. Basically, as far as I can understand this, it's just there's a difference between the, I guess, the quality of the answer and the accuracy of it. Or there's not even a great way of saying that. When I think about loss, I think about maybe the model's confidence in the accuracy. It's going to give you an accuracy, but the higher the loss, the less confident it's going to be about that answer. Again, I think if you have a general understanding of what it is, that's more than good enough for now. We are not here to become data scientists, and we're not even really here to become ML engineers. We want you to feel comfortable enough to work with these processes so that you can have an idea of what SageMaker is used for. Now it's used for all sorts of different things. It's one of the largest AI platforms that AWS provides next to Bedrock, I would say. And so it's not really just a service, it's a suite of services. There's a lot to unpack with SageMaker. And while we only covered for a few weeks, the basic emphasis for us is to be able to use it to train models and to integrate that somehow into our orchestration. So what we'll be doing in the lab, we'll be taking everything that we've just briefly discussed right now, and we'll be putting it all together into a sequence. And then we'll be running through that sequence to calculate the probability of whether or not water is potable based on some data that we pass in. So let's begin. You should have the lab pulled up. Pull up your VS Code, your terminal, and let's create a new directory. I've already got mine, but I'll just take a demo, do this well. You could call it binary classifier. I'm going to make my number 2. You are going to go into that directory. you are going to set up a virtual environment. So let me deactivate this one. I hope I don't regret this. And you are going to do your Python dash m venv venv, passing in the name to your module, your venv module, and then you're going to source it to activate it. All pretty vanilla, all stuff that we've done before. And once you've activated it, then we're going to install some packages. Same as the ones we installed yesterday, but with a few additions. And if we look inside of our lab, that should tell us what these additions are. So we are going to have Jupyter, IPY kernel, IPy kernel, Torch Vision, Pandas, Scikit, Learn, and Matplotlib, math plotting library. Okay, so let's install all of that. Oh no. Oh, I have an H in here. And once you've got that installed, now you are going to run the IPy kernel install, passing in some params like a user, name, display, and then we could use the Jupyter command to verify that it's been created. Cool. So Python -m IPy kernel install user. Oh, look at that. It's got all that stuff for me. I'm going to name this number 2, and I'm going to hit enter. Now that I've got, now that I've hit enter, I can create a new file. So I'm going to use code. I'm going to create binary classifier -2 dot IPYNB for notebook, NB for notebook. And I'm going to hit enter, and open up that file, and I'm going to select my kernel that I created. Except I think it's gonna, yeah, it's not showing it to me right now. So I'm gonna go ahead Command Shift P and hit reload window, and that should allow me to select Jupyter kernel and the environment that I want. So binary classifier 2. Okay, so that's what you got to do to get set up. I'm actually going to deactivate this. I'm going to go back to my first one. Source and activate. And I'm going to do the same thing here. Got to reload again. Okay, cool. Oh, wait. No, that's not cool. That's not the right one. Why is it doing that? I mean, maybe it doesn't really matter. Let's see. Oh, maybe I hit refresh. Let's see. Maybe it won't care. Maybe it will not care. Yep. I'm in the wrong environment, so it's not liking that. So, oh, maybe if I, let's see. Yeah, let me rerun this. That. Now if I reload. Cool. not so cool. It still didn't run. What I do wrong? Oh, did I skip this? No, I didn't. Yep, I skipped this. All right. Now that I'm set up, the first thing I'm going to do is I'm going to add this code block, this first code block, importing our libraries, and some print statements just to verify. It should output my PyTorch version, my Pandas version, and now I'm good to go. Now in my next block, I'm just gonna throw in a very simple example of a binary model. We are going to instantiate the sequential and the sequential class, and then we are going to pass in some values. Here we're passing in linear. We're taking 3 inputs. We are going to output 4 inputs. Use case for this. I think earlier I mentioned, okay, should a person be approved for a loan, right? So these 3 inputs that we take in could be things like basically data that we know about the applicant, and they could be represented by
Income, credit score, something else.
yeah, exactly. Debt ratio, right? So we will take those values, we will combine them in a various number of ways. Right now, again, it's sort of arbitrary. We're really just picking four. It doesn't have to be four. It could be any number that we want. But just for the sake of this example, we're using four. We're then going to use ReLU. And somebody tell me, what does ReLU do?
Introduces nonlinearity. It's an activation function.
Okay.
I believe it cuts off everything below 0. I don't know. I looked at a
Yeah.
graph of it. It's a lot more illuminating than talking about it.
Yeah, but that's the key part there, removing everything below 0, right? So that's gonna give us an easier range to work with. Because if we think about, let's say, I don't know, trying to attach values to these things, it's just easier to work with positive numbers than it would be to work with negative numbers. Because what would it mean, for example, to have like a negative debt ratio? I don't know. So we're going to use that just to make the calculations more sensible, easier to work with. And then we're going to use linear again to take those 4 outputs and try to squash them down into one output. And then we're going to run that sigmoid function on that to translate whatever that value is into either a yes or no value. And let's see what that looks like. I don't know, is it doing it again? Why did it do that? Come on. Okay, cool. Looks like it gave me an output. Okay, so it shows us that we have 3 features coming in, 4 coming out. We run ReLU, then we have the 4 features coming in, 1 coming out, and then we run the sigmoid on it. Now, yeah, it's very simple example. I don't like this example. It, it'd be a better example if it was showing us a tangible end result. But I guess the focus here is to see what a binary model looks like. So there it is. There's a very simple example with very arbitrary selections. Now, what output are we actually looking for? We're actually looking for probabilities, right? So if we run that sigmoid again on like maybe just like a different set of numbers, we could grab the probabilities out of those outputs. And this is why I wish this example was better. If this example was like directly connected to this, that would be a little more tangible to work with, but here we are. So here we grab our probabilities, and then we could loop through those, and we are basically taking a raw value and we're converting it into a probability. So let's see. I guess this is just a way to test that sigmoid. I guess we're just running that sigmoid function and we're seeing that, okay, it's doing its thing. It's actually converting numbers into probabilities. Right. We talked a bit about how that works, right? We talked about how negative numbers will convert into values between 0 and zero point 0.5. And a 0 will be a flat 0.5, right? So when the value that we pass in is negative, it's going to fall between 0 and zero point 0.5, and then vice versa. When it's positive, it's going to fall between 0.5 and 1. And that's how we can essentially from there translate it into a yes or no answer. Making predictions. So I guess it's really just flattening that number even more, right? Okay, so we have that hard like 0.99 or zero point 0.5 or 0.26. Now, what does that mean in terms of a prediction? A probability is just a chance, right? It's a percentage. But to flatten it to a yes or no value, well, we'll have to round it up or down. So that's really all this is. And then loading some actual test data. So I don't know if you guys worked with this at all yesterday, but basically when we have our data, can somebody tell me what the shape is?
I think this data has 3,276 rows and 10 columns.
Exactly, exactly. And those columns are, all right, I'm not sharing my full browser. Let me see here.
Is that it right there? pH, hardness, solids, chloramines.
Yep, it is. Yeah, so
Those are the headers of the columns, I guess you'd call it.
yeah, exactly. And if I was sharing everything, you'd see in my browser that there's that many rows. I'm just going to switch right now just so I stop forgetting. Let me just clean this up. Okay. Just easier way to switch. Is that what this is? No. Okay, that's this. Okay, cool. Nice. All right. So yes. And again, like earlier, mentioned earlier, there is an entire repository for you to grab these data sets from. And that was what was linked in the Zoom. So you've got all sorts of stuff like you could play with a Dogecoin if you wanted to, Ethereum, um, Elon tweets, apparently. Nice. Okay. So all sorts of fun data here. Let's see. What else? We are, where were we? Right, we were loading this data set, and I think all that is just going to show the output. And now that we have that data set, we could run some additional functions to see what's going on with that data. We could run head to see like the first n number of rows. 5 is a default value, so if we run this by itself, we get the first 5 rows. Now, if we pass in a number, then well, let's not go that high. Then we'll see that many number of rows. Describe will let us describe the data, and it's just going to use these descriptors, right? So your count, your mean, things like that. And it's going to run it on every column, every numeric column. So that is. Let me actually make sure I clear all these outputs. Okay, so it's a little cleaner. Okay, check missing values. Right, we talked a bit earlier about how data in the real world is not always going to be perfect. So cleaning your data and optimizing it can get you closer to getting better results. Not always, but usually. So let's run this, and we see that there for these columns, there's like this much missing data. 23% of our sulfate column is missing. And so from there, we could decide, well, what strategy do we want to use to deal with that? Earlier, we talked about just using mean. And if we run things like this, we can see hard value counts and get a feel for some distributions, and that should help inform our decision from here, right? Here we're using that fill NA method that I mentioned earlier. We're passing in the mean, so that's going to fill in all of the missing values with the mean of that column. So let's run that. And now we have no more missing values after running this. Separating our features and our target. This is basically how we can specify not just the inputs, but the outputs that we want as well, right? We had here, we are dropping one of our columns. So we're going to be going down from 10 to 9 columns, and we'll still have that many number of rows. Now, when we do our target shape, we are essentially specifying that we want one output. Does anyone want to take a guess as to why we're doing this with no value specified versus having a value? Let's see. I should have made a note.
Is it is it because we don't know which data columns attributes are our features and which are predictable based on those features yet, aka the targets. So we don't specify, but we rather let the math do the math and help elucidate us.
Yeah, that's right. It basically if it's not like a I guess if we don't know the end result, then we can't specify the end result. So we just let the math do its thing.
So,
Now,
so was the question why we're dropping the potability column?
oh no, more so like why we like if we see this target shape here, we have this comma with like nothing following it. So basically the shape just has like one dimension.
And why is that?
Well, it's going to affect like the output of the data. So basically, if we did specify it, if we had like a one there, for example, we would still be getting all of that same data, but it would be organized as like a two-dimensional tensor versus a one-dimensional tensor. And like this is where I'm sort of wishing I had actually taken some written down like how I was gonna like adjust this to demonstrate that, and I'm blanking right now. see if I could try to remember that, but for the end of the night, and maybe I'll go back to it. Let's see. So this is again though, like ultimately we're separating our inputs from our outputs. And from here we can normalize our features. And we talked about this earlier as well. We talked about using the standard scaler to standardize the way that we're handling our data. So we're fitting different kinds of data into one standardized measurement. So let's run this. And before our scaling, we had these different values, and now we can interpret them along the same scale in this way. Let's see. Then we talked about training and testing splits. So here we take, let's see, we have 20 samples and 656 test samples. Are we specifying that? Okay, so test size. Okay, so we write the percentage here. We're taking the data set and we are saying reserve 20% of this for our test. So we go down from whatever that number was before, 3276 down to 2620. That's how much we are testing, or sorry, training, and we are reserving 656 for testing. Now we can use PyTorch to convert all of that into tensors. And let's run this. So our training shape is going to have, again, this many rows and 9 columns. And then we'll have, for our output, that same number of rows, but with 1 column output. Let's see. Okay. Creating a data loader. Oh, right. Okay, so for this part here, we are creating a data set, and then we're also creating a data loader, and this will allow us to batch our data into different sets, right? Instead of testing all 2620 rows at once, we could specify a batch size. And so if we want to do these in sets of 32, then that's going to result in 82 epochs. An epoch essentially being a run or a cycle or an iteration going through the entire sequence of that data. So if you do the math, 2620 divided by 32, you would come up with 81 point something, something, something. That rounds up to 82. And that is, again, somewhat arbitrary, right? Like we could change this number if we wanted bigger batches, and we would just have less epochs, right? So if I hit enter, now we're down to 41. And that's what setting the batch size for a data loader does for us. Ooh, and right, we could also have other parameters like shuffle to shuffle that data around. So we're not dealing with that exact same data in the same order every single time. Okay, putting it all together. Now we can build the actual model. We can call it water classifier because that's what we're working with. Again, like mentioned earlier, we are working with the base module. We are specifying the actual sequence that we want to run with. Here we have the 9 columns, the inputs that we've selected because we've dropped potability. And let's just choose an arbitrary number like 32 because we're going to have a batch size of 32. And then we will run ReLU on that. Then we will run another linear algorithm to output those 32 inputs into 16 outputs. I'll run ReLU again. I'll run linear again for a single output, which we will then run sigmoid on to convert into a binary value. And from there, we can define a forward method so that we could do like an initial run, and then we will assign that class to a variable, which we can then call to instantiate that class. So let's run it. And now we see we have our instance of the water classifier class. It tells us that it has this many layers running inside of its sequence. And for each step of the layer, it will do one of these things. It's going to run linear, it's going to run ReLU, etc. Now, let's see what we ultimately have. We have 865 trainable parameters. And if we tweak the numbers that we've had earlier, we could change this, right? So basically, if we have, for example, a larger batch size, more outputs, we run that, we run this again. Now we have twice as many trainable parameters, right? Because we have twice as many outputs. And that may or may not improve our results. We'll find out when we actually start to run through the data. So let's first set this back to 32. Let's hit Shift Enter. Let's hit Shift Enter here again. So we're back down to our 865. Now let's test our forward pass. And we have this initial run. Again, like the forward pass is kind of like your trial run or your pop quiz. You test before you even study for the test, and you see how well you do. This gives us the ability to predict that we are going to have these probabilities at the end. So it's not looking good. The water's probably not going to be very potable, so don't drink it. And now we can calculate loss against the accuracy. So why is it doing that? I think I'm missing something here. Let's see, what am I missing here? There's no kind of print output. So let's see. Let's just add one. I don't know. Let's just see what happens. Okay. Also print this. Okay, so that's just calling the BCE loss class. And then there's a bunch of data here that I don't even know how to interpret. So if anybody knows, feel free to jump in. I think we covered this in full stack and it's totally like beyond me right now. Atom is just an algorithm, right?
Yeah, what's the definition of it? I think it was right there in the lab, wasn't it?
Oh, was it?
I could be wrong.
Yeah, there it is. Adaptive optimizer works well out of the box. And so that is the output. This is all the data that it gives us. And let's more or less trust in, in what it's saying. But now we could run this training loop, right? We could specify the number of epochs. And again, the number of epochs is like the number of times you're going to run through that data. The higher the number, maybe the better your results. At some point, there's going to be diminishing returns. And so there's no point in like just going that high. Let's see what we get with 100 epochs. We are training, and we are getting an accuracy of 76%. Now, with decreasing loss. So where's that being used? Hold on. There's the optimizer. Okay, there it is. And then okay, so it's doing a bunch of magic that I can't I can't conceptualize right now. And basically that's going to help inform us in how we're going to want to adjust our data moving forward, right? If we knew what we were doing. And so let's run this again with more epochs. We could see that with more epochs, it's continuing to increase its accuracy. Uh, where is the point that we hit diminishing returns? It looks like it's starting to just sort of stagnate here at about 85%. Once we get to like 1,000, it's pretty much just staying at 87, now 88. So 1,000 versus our initial 100, we do see some difference in 8% accuracy improvement. That's pretty good. I think that's still pretty significant.
But that's
Let's
just training accuracy, right?
right, right. Let's see though if
And now you run the risk of overfitting,
hmm,
right?
yeah,
You can make this thing really good at predicting what it's being tested on, but or what it's being trained on, but when we actually test it, the accuracy might not be so good.
right, right. Again, it's kind of like
The Amazon analogy from earlier.
right,
If the
exactly.
test was the same every single time, yeah, I could memorize every answer, but then as soon as you ask me anything slightly out of that, it's gonna throw me off and I'm gonna fail.
Exactly, exactly. So 100 is probably a good place to keep it. It's probably going to be running for a while now.
What's that? It's that same 80/20 rule you brought up earlier. It's like the vast majority of the gains you're gonna get are right at the beginning, and then putting more and more effort into it, you're gonna get diminishing returns, if not actually do negative for later testing.
Exactly, exactly. Yeah. And you'll see parallels to this too in like other ways that you interact with AI, right? Like when you're, for example, feeding it way too much context, that's going to pretty likely diminish the quality of the answer that you're getting, which is why context management is very key when working with agents. I wish, I really wish our curriculum covered more, and maybe it will in the future, things like the agent loops, because I think it's getting interesting to read about how like Anthropic and OpenAI and like just other organizations are solving some of these memory and context issues. I think with Cursor, I saw something new recently where it started to collect the things that it would learn, right? So if you're running an agent in Cursor, there are times where it will say, I'm learning something, and it will store that in a file called learn inside of a Cursor directory. Claude allows us to do things like create a .claude.md document inside of our root directory of a project, and it's going to always check that. You could have h.md inside different directories, and it's going to know to like um, reference that from time to time. But if you're flooding it with way too much context, it's going to forget to do those things. It's going to forget to check, or not really forget, but
It,
it's going to prioritize some things over the
it
others. And
it's gonna get so watered down, like
exactly,
because I'm sure everyone has, but I've had that happen to me where I went on for way too long in a GitHub Copilot session, and I could just tell. At one point I started feeling it going downhill. I'm like, I should probably stop and start a new window, but I was like almost done with something, and it just fell off a cliff, and it could not figure anything out. And I was like, oh man, I should have reset a long time ago.
yeah. I I do that way too often. Like I get
Yeah.
some this I guess some cost fallacy kicks in, and I just want to
Yeah, yeah, I just got to get this finished, this one part, and then I can be done, right? Yeah, but no, it leads you into that trap.
yeah.
I'm surprised. I mean, I think Kathleen mentioned a couple weeks ago something about Claude having some sort of workaround for that, and I feel like that'd be maybe I've been missing something obvious, but I feel like it'd be a fairly simple like something to check when the context window is just getting too big. It should warn you just a little bit ahead, like, hey, you should probably, make a summary, start a new chat window now, or automatically do it in the background or something. I don't know.
Well, I know Cursor does that. It has like a circular like fill bar. Like I forget what those are called, but that shows you how close you are to reaching 100% context. And when you reach 100%, it's going to automatically compress the context. But you have no control over how it compresses it, right? For all you know, it could be throwing out the good
The good
data.
stuff and keeping crappy stuff.
Exactly, exactly.
Yeah.
So having and finding ways to like manually control these things is like where I think the challenges get really interesting for AI developers versus ML engineers, right? With machine learning, like you have these algorithms that you're working with, and you're focused primarily on training, but the majority of the people out there that are working with AI are probably going to be working with like pre-existing, pre-trained
Yep.
models. And
Yep.
so now you have this sort of this shift where you could sort of think about machine learning as being the back end to AI, right? You're training a
Hmm.
model before it really faces the consumer market. And as an AI engineer, as an AI developer, you're more concerned with how to optimize after the LLM has already been trained.
Yep. Yep. Yeah. Like my wife, she has no interest in machine learning whatsoever. She would just walk out of the room, glaze her eyes over. But she uses ChatGPT a lot for stuff, you know? And so she's a perfect example. I assume there's a lot more of my wife on the planet than there are of me, you
Yeah,
know? So there's gonna be a lot more people wanting the LLM to do its little things versus being interested in actually training a model in the background.
right, right, right. And if you're interested in like entrepreneurship or startups at all, like there's a booming market for this, like optimizing front end tools for users.
But that's the thing though, is that it's the process in itself is starting to become more democratized, and as in it's starting to become a lot more easy where the everyday layman can train their own model.
Mhm.
It progressively getting to the point where they make it a lot more easier.
Oh yeah.
Cool. So we reached the 97% accuracy. It's probably not going to be that accurate. Let's see where this gets us. Okay, so this now will let us plot that data. So shoot, what was happening? What? I've never seen this before. Control is disposed. Maybe we had too many too many epochs. Let's bring that back down 100, and let's see if it will. Okay. All right, much better. Whoa, that is very different from what I was seeing earlier. Wow. Okay, let's clear everything. And okay, because I wanted to make a point here. Let's see. I might have to, I wonder if I could just clear up till here and rerun or
You can actually do that if you go to the right. You can actually run from that particular part up. Yeah.
this one.
It's
Sure.
yeah, that one.
Yeah, but I don't know. I'm still getting like these high values. I want to like reset completely. So let me restart. Yeah, let's do that.
So every time you were running that, it was rerunning the already trained model again. It was adding some training to it, which is why it was starting at such a high percentage.
Yeah, it's like adding, it's like doing like a digital epoch.
Okay. On top of the ones you already did.
Hmm.
So it's not a fresh model. It's training. Okay.
Right. Why is it so?
Jupyter notebooks are so weird to me.
Let me try right from the start.
Does that make sense?
I don't use Jupyter notebooks nearly enough to be very comfortable with it. So like I'm not even very good with this interface. Like I don't hover's not telling me anything. Oh, there it is finally. Except oh nice. Okay, I see, I see. Hey, why does it keep doing this for me now? Shoot, what did I do?
I don't think it has anything to do with your actual model. I think it's just Jupyter Notebook by itself.
Right, but like
What does that mean? The notebook controller is disposed.
I don't know, like did I just like have it running too much shit?
Mm, mm, controller.
ChatGPT says the Python kernel you were using got killed, disconnected, or invalidated, and VS Code doesn't know how to talk to it anymore.
Validated. Interesting. Okay.
It
let's
says if you restart the kernel, that might help.
Yeah, you just did that though, a couple of
yeah.
times.
Oh, did you? Okay. Then reselect the Python interpreter and re Control Shift P reload the VS Code window.
Okay, just did that. And
Okay.
okay, so far so good. Oh, but it did run all. Whoops. All right, let's see. Where are we? We're should be back down. Okay, cool. We're back down to like a lower number. So there we go. That's closer to what I was seeing when I first ran this. And basically want to go back to this just to go back to that point about, the 2080 principle, how we have our biggest spike early on, and then we see essentially a linear climb afterwards, linear decline down here. So now that we have the training accuracy, let's actually evaluate with the test data. Okay, and so our test accuracy is 65.7%, which is lower than the training accuracy. And now we could do additional things like throwing in a confusion matrix to try and improve or further validate our confidence in the model. So if we were to run this, there were these predictions against the actual values. And this basically tells us, or we could interpret this as being 55% of predictive positives were correct. And of those actual positives, how many were actually, I guess, I'm not sure how to interpret that. Recall 42% of actual positives. How many did we find? I guess, yeah.
Yeah, so the precision is like it says of all of the predicted positives, how many were right?
Mm-hmm.
So 55% of the time you predicted a positive, you were actually right about being a positive versus recall is of the actual positives, how many did we find? Because it doesn't find all the positives.
Yeah, what is it? Yeah, accuracy, recall, and then F1
Yeah,
uh
you can use those to score
for the
because
score
it's
itself
not just like
becomes
a
one.
single score that tells you the whole thing. You got to look at a couple different dimensions.
Mm-hmm.
Yeah, I'm trying to remember the formula, but it's there's a reason why I think they call it a confusion matrix. It gets really confusing.
Also, just so you know, in the lab that we have, or at least the one I have, we
Mm-hmm.
don't I don't have those plots like you showed.
Really? The one that's on
Yes.
the,
Unless I'm on a different repo. Maybe I missed it. Hold on.
yeah, let me double check.
Oh no. I must have just missed it.
Okay. Okay, and then with our individual predictions, we can select out of 10, do some logging to try and compare. And these are just various ways to try and test and validate and evaluate the results. Once you have all of that, you could save the model. And so that's what we did here because I ran run all. It's saved to water classifier.pth, and the scalar was saved to this. And now we could run the entire model, loading it and using it. we even snatched it as a class before, but now we've saved it so we could load it. We could load basically the state that we had saved before, and then we could run an evaluation on that. And with that, we get a probability of 31%. It's predicting that it's not potable, and that is our results. I'm not sure what this warning is. If feature names is none, was fed with does not have valid feature names. Okay, I don't think that's very. I don't think that's too important. But that is more or less how we can create our own binary classification model. Any questions? Cool. So I'll I didn't actually upload a challenge, but basically just go ahead and try to play around with some different data sets. You'll probably have to grab one of these other data sets and plug it into your notebook and step through again, and that should give you some various perspectives on how this is actually working, right? So like how does it take these data sets and how does it create its predictions? You'll probably want to look for data sets that would fit into a binary classification, like a yes or no output, because I don't think all of these are gonna fit into that. Elon tweets, I don't know if that's going to, wow, that's interesting.
Guy must tweet a lot.
Yeah. What does it do? This is just a conversation, ID, created ad. It's just, I guess, a list of the tweets. Probably not something that you could plug into a binary classification. But yeah, any of these other data sets, just look through them, see if there's anything that you could play around with. Okay, I am gonna open up breakout rooms. We've actually been here for a while, so go ahead, take a break. Let's see. We could have a, did you guys have a stand down last night? Okay.
People were doing their assessment.
Right. Yeah, if you haven't done your assessment, let's get that done. We're at a point where really I would say just get it over with. Um, yeah, just to get it off your shoulders, you know. So if you haven't done it yet, just consider going forward with what you have, and chances are you'll probably do better than you might have thought. I think a lot of times students see like these large lists of requirements, and it can get very overwhelming. But there's a lot of bonus points, a lot of opportunities to do things in various ways, and really you just want to. I think if you talk through the assessment and the project and what you have, you'll you'll find that you're not missing as much as you might think you're missing. So if that's what's stopping you from like going forward and presenting, just try to reach a good stopping point sooner rather than later, and ping me whenever you're ready.
All right, I'll ping you tonight, Julius.
Cool. I'm going to open up breakout rooms now. Feel free to take a break. And again, let's do a very quick stand down, like around 9. If anybody wants to run through one of these other data sets that they find and talk through the whole thing, I think that'd be a very good exercise for testing how well you are grasping these various um, algorithms and concepts.
Julius, you may have covered this at the very beginning of class, which I missed, but are we going to be using this level of coding in, more in the course? or is this week, sort of going to introduce these concepts to us, and then we're going to kind of switch back to the pre-made models and the AI engineering side of it?
Yeah, you'll have that option when we get to SageMaker. Like, you don't have to put a lot of emphasis. Like, it's an option for you, right? Like, you can definitely dip your toes into training and optimizing some of these models, but there are also pre-trained models available in SageMaker they could play around with. We really will be more focused on the pipeline, on the automation and the delivery of these various tool sets. Like, how do you provide people the way to train and optimize their models if they wanted to, et cetera. And you'll have flexibility too in like how you integrate all of this into your capstone projects.
Okay. So there won't necessarily be criteria in an assessment that is associated with how well we tuned our hyperparameters.
Right, exactly.
Okay, cool. Thanks.
Right on. Cool. Right, opening up breakout rooms and let's meet back at 9. Am I still recording? How do I stop?